So this is a Francis turbine, I guess. Water comes up through the middle and shoots out sideways through the blades. Just happens to be sitting on the ground outside this power plant. So this is on the Waikato River. There's a dam upstream that takes the water behind it in a canal, and it drops down through this turbine hole and then back into the river, and then goes downstream. Yeah, okay. This is the lake. This is the sea, and everywhere along this is dammed along the length. It's kind of stair step, and it's a turbine hole, I guess. Yeah, with three. I think there were 3 turbines, perhaps 4. Can't remember. And the students, small class, maybe 8 students that time. This is 2019, probably. Yeah, it is. We were COVID cancelled in 2020, so we didn't go. So, yeah, fine. So that is an aside. So I guess the main thing to look at was probably this Francis turbine. So I guess this is one out of that dam, out of these the housings. So the water comes in and comes up from below and shoots out the sides to generate power. So, yeah, fine. Okay. So, I'll start these before we get going. Can you see that? Is it too dark? Not looking.
It's just
yeah, fine. Yeah, well, I think it's low. It's probably 420 or 720, 460 is it, or 720 resolution. Perhaps all YouTube stuff is. It's certainly not 1080p. It's good that I don't actually have to turn down the lights for the stuff. So, yeah, I guess he's putting, probably should be using gloves if you're handling liquid nitrogen. I think that's what he's handling. And he's going to put it in water, warm water. It'll evaporate the liquid nitrogen, expanding as it goes. And you have a little engine working as a result. And so what we'll talk about today is, after we've kind of done our recap, is talk about rotational moments of momentum, not linear momentum, but moments of momentum. And it's relevant for us because lots of things that we do to convert linear kinetic energy into rotational kinetic energy is to do with energy conversion. So one would be linear impinging flows on wind turbine blades, to turn them into rotational motion. Flows through a turbine, so linear flow of water from an upstream dam with high velocity, gained exchanging potential energy in the upstream portion for kinetic energy downstream, and then that linear kinetic energy converting it to rotational energy, which will run a generator, which is just an electric motor backwards where you power the rotor and use the armature to generate electricity rather than putting electricity in it to generate motion. So I'm sure you know all that. And so some examples of that would be, this is not a bad video. Along the lines of it's in German, along the lines of the dammed Waikato in New Zealand we just talked about. This is, the principle of it. Of course, in this transitional economy, one of the big things is storage. And so grid storage that's big enough to take lots of power to make up for power when the sun doesn't shine and when the wind doesn't blow, is to use things like pump storage. So you have an upper reservoir, lower reservoir. You pump up when you have excess power into the upper reservoir. You run it downwards when you need the power at nighttime, say, if you need it when the sun isn't shining. And the part in the middle of this, which either serves as the pump to take it up to the pump storage or the generator to generate electricity back from it as it comes back through, is a turbine. Again, changing linear kinetic energy, half mv squared. You'll notice the similarity with the term in the Bernoulli equation. So linear kinetic energy as it comes down this pipe, so from the upper reservoir to the lower reservoir to generate power, or to pump it from the lower reservoir to the upper reservoir. And of course, no machines are 100% effective, so you lose power going up and you lose power going down because of frictional losses. And that's what we'll start talking about in week 8 when we talk about thermodynamics, conservation of energy. And everything we've done so far has assumed that the viscosity is 0. And so they're perfect engines, go from upstream to downstream. You don't lose any energy in the form of heat by frictional losses along its length. And that's a big part of the systems that we have to consider. And so this would be a typical turbine to generate electricity, or a pump to pump fluid upstream by using electricity. They're just working in reverse. But both have an energy penalty in doing it, but you hope that the energy penalty isn't too great. And of course, I didn't realize this until quite recently. In Pennsylvania, up near on the Allegheny River in northern Pennsylvania, there's a small pump storage scheme that does exactly this. It pumps water up from the Allegheny River, probably top of a plateau, so I imagine it's probably 1,000 feet, 300 meters, stores it up there, then runs it down when it's needed. So we have that kind of stuff close by here, much bigger schemes elsewhere. And so it's one of the answers to grid storage. You've seen this, of course. Part French, disponible à eBay, available at eBay. This is a Pelton wheel with a little air jet from a compressor, I guess, off to the left-hand side. Just running this thing on a perfect bearing. And so we've seen that. And so again, linear kinetic energy, high velocity out of the compressor jet, turning into rotational. I guess we haven't seen this one. I took the one from New Zealand that was the Pelton wheel out before I posted it. I guess you're not looking at the postings. I'm not sure how many people are looking at the postings. I guess there's so much content online on our website for multiple years that don't change very much that I'm not sure that we get 120 views for the 120 people in the class. But this is interesting, linear motion of the river pushing on these fins, these aluminum fins on the side to turn this thing. And all it does is it lifts water kind of in an Archimedes screw to be able to move it from the stream across to the right-hand side to the ditch to be able to store it for personal use. So it's using the kinetic energy of the river to drive the thing around. Quite a clever design, really. Very simple. I guess you could go to Lowe's and get all the components of that quite easily to do that. That's kind of cool. And I can't remember what the last one is. Is there a last one? Oh, yeah. So this is useful to look at because we'll look at this today. We used to have a better one with... So maybe you all look at cats fighting on YouTube, but this is the equivalent of this. This used to have dogs running around a sprinkler, and it seems to be a sales video, so I think I need to skip to the end. You'll get the rough idea when we see it. Yeah, so you've seen these things. So these are sprinklers to be able to get your garden in order when you just laid seed and straw. And of course, linear feed of water into that, being squirted out of the ends. You can change the attitude of the squirters, the nozzles, I guess, to be directed upwards or downwards. You could have them at an angle, or you could have them 90 degrees to the yoke that connects them. And so the question is, how do we understand that? How quickly will it rotate? And we can use all the principles that we've already used in linear momentum to basically understand that. So that's what our journey is to be able to do today. So today we'll kind of finish a module with momentum transfer, so conservation of mass, conservation of momentum. 8 will be a new group, so the next midterm will stop on the material that we've talked about today. And the next midterm will actually include a question from, Wednesday and today. And so it behooves us perhaps to understand this stuff. So I hate to hit you with that this morning, but that's just a reality. Maybe clean up this, just to note this. Well, we talked about linear momentum last time. I got a couple of questions at the end related to kind of sign conventions. And so it's probably useful to mention that. I thought, actually, doesn't work. I recall that last year's video for this 7.2 class had a night. You can see the inner workings of my mind when you look at this, but I thought that 7.2. The videos don't change very much from year to year. You'd have seen these, but there was kind of a nice. No, I guess it wasn't this one. It was this class. I'm not going to do this year, but the class last year. Am I back in? Did it not come up? So yeah, you can see that we do things similar each time. But last year I thought there was an interesting summary that I did. The 3 things we talked about last time. Remember, we did the jet lev, we did the moving vane behavior, and we did moving non-steady with the gas cylinder. So they're summarized here in terms of the equations that you need. They're the same equations that we've used throughout. And it just gives a rationale of what it is in terms of also calculating energy from them, as we did in the last part, right? So I only show it on here instead of YouTube because I can run it at higher speed. And so this is not a bad summary, I think, of the things that we wanted to do. Okay, is that right? I can run it backwards by doing this. And so that's worthwhile looking at. But just to summarize again on the material that we have from last week, was to note the questions were how, when you do this for the vane and for the gas cylinder, how do you choose these different directions? So you have to be careful that you define things in terms of the coordinate directions. The equations that you use, this relative velocity of the fluid coming out of the system and relative velocity of the control surface, have to be written in terms of the Cartesian coordinates. For the jet cylinder, or the gas cylinder, positive VCS is in the positive x direction. We don't have a velocity in z because we're not going uphill, but if we did, positive VCS in the z direction would be upwards. That's just our sign convention. And so the equations that we've written depend on that. We can draw the reaction in any direction we want. This reaction could be pointing to the right or to the left. It's just that when you use it in this equation, because it's pointing in the positive x direction, it's got a positive sign in it. If we drew it in the opposite direction, it would have a negative sign with it. And when we went through the calculation, we'd find that the resulting sign of the reaction was in the opposite direction. So you have to be a little bit careful with the sign convention. And the other thing about the sign convention is to remember this box, right? So we have, for conservation of mass, we have sum of forces, Cartesian directions. We have mass flow rates in terms of the relative velocity times the area of the fluid coming out of it. And when we do that in terms of conservation of mass, we always do it relative to the outer normal. The outer normal allows us to be able to gauge the relative direction. So the sign convention is for mass flow rates, a flow rate in is negative because it's opposite the direction of the normal to the boundary. I draw that on here. The normal to the boundary would be in this direction on this surface, right? So this is in the opposite direction. They're counter to each other. And so if you did the dot product, we haven't messed around with that very much and wouldn't have to, then this is negative in and positive if it's coming out. So the terms that impinge on the mass rate of flow, which are either this in the conservation of mass equation or this in the conservation of momentum equation, always have this sign convention. And the terms which relate to the kinetic energy are always with respect to the Cartesian coordinates. So this one is in the direction of positive x, so this one is positive, and this one is also in positive x, and this one is positive. And so you have to be cognizant of when you use those here. So think about it and look at the things. We can talk about it again if you want to, but that's kind of important. And you can probably get a feel for these because you could understand that, you know, what the basic lesson of what we talked about on Wednesday was you have two conditions. You either hold the vane static and impinge fluid on it. That gives you the maximum reaction force because the velocity of the control surface is zero, and therefore the product of this mass rate and this flow rate is maximum. Or the velocity of the control surface has to exactly equal the velocity of the impinging fluid, in which case there's no force applied on the vane because these cancelling each other out allows this, is the only way that this term can be zero. And so those are the end member conditions that allow us to get these two cases. Either you hold it static and the velocity is zero, or you let it go at the velocity of the fluid and the force that you apply is zero. And there's some curve that relates these. You could do something more sophisticated. It's not a straight line, but it has to be something between those. I don't know exactly what it looks like. But a good bet of how that might be is to look at power coming out of the system. And for power, you have to have a force that's resisting behavior multiplied by an actual velocity. If the force is absolute, that it stops it, you get no power out of it. And if the force is zero, even if it's a high velocity, you're not doing any work against it, and therefore also the power is zero. So that's kind of what that's a recap. So be cognizant of that. You notice that I don't really go through my own notes anymore. I kind of rely on writing it down. I think it's just better that way. So, I don't know. Questions before we go? It's rare for me to ask for questions. Rare for me to get them. Thank goodness. All right. So that's kind of the 5-minute summary. So this is our linear momentum equation. We've replaced this integration really by a summation on the boundaries. If we do the summation, then we can kind of get rid of this, ignore this normal term because we take care of it by looking at these directions. And all the dot product says is if the vectors are in the same direction, their vector product v dot n is 1. If they're opposite directions, it's minus 1. If it's perpendicular, it's 0. So that's the behaviors that we would look at. Okay, so the rest we don't need. All right. So moment of momentum. What do we want to talk about? So what we'll do, and my cheesy way of doing it, is to be able to note that what we looked at. Let me do it here. What we looked at before was our vane, V-A-N-E. And we could look at water coming into here at some velocity, V static, and it would go through this, etc. And what we could do with this is that we could also look at a velocity of this control surface, which is called VCS. And I guess we could also look at the impinging velocity on this coming into this, which is W. And of course, the sum of these two is V static in case you're in any doubt about that. And we could think about this in terms of our Cartesian coordinate system, x and z. So this is linear momentum. And the equation below that deals with that exactly. So this is an integral with a dot product. We can throw away the dot product, and we can use this plus minus convention that we just talked about. Then we don't have to worry about this, and then this just becomes a summation. So the expression we have is W plus VCS. I'm leaving some space times rho WA is equal to sum of the forces. In this particular case, it would be in the x direction. So these would be the velocities in the x direction. This would be the in or out magnitude. And we could use that to solve the linear problem. If we wanted to, we could think about this as a rotational problem. And so if you think about this cart instead of being on rollers, and you can think of these, I'm going to get rid of these radii in a minute, but if you think of these radii going to minus infinity, then this is still a linear problem, because as this becomes infinity, then the arc, the turning of the arc is so slight that it's essentially a straight line. So we could think about it as that. So we'll talk today about using the idea of this. We won't use such a long line, but what we'll do is we'll work with this on a shorter line, R. And if I do that, you could imagine, I'm not sure how rigorous this is, that we could take this equation and we could multiply both sides by r. Just a number. And it turns out that the moment of momentum equation, rotational momentum instead of linear momentum, is exactly that. It looks a bit more complicated. Perhaps you can see a connection between Reynolds transport theorem done for the linear momentum with this. This is a rotational velocity that's been added, multiplied by some kind of velocity with all the other terms. And this is a rotational velocity multiplied by the force. It's probably not completely rigorous what we've done, but it serves to make the point that really it's not very different at all. And so we're going to do an example for the sprinkler that does that. And this turns out to be, if this is a dot product, then this is a cross product. You've seen it in your past. You might not remember it. I don't from time to time, and not at instant recall, but we can talk about these things. And so the utility of this is that we can look at this term here, which we'll call torque. So the product of a force times a lever arm. So this is a force that would be acting. So this would be the force in the x direction, which would be a reaction to this. Again, we can choose to write this in any direction, but we have to be mindful of our x and y. This is a torque, product of force times distance, just like a torque wrench has a force you apply on it on a bolt multiplied by the lever arm. And this is a, actually I don't know what you call this. This is a cross product of the velocity and the lever arm. So the torque that is placed on the shaft is equal to this whole term here. So this is the torque, and I guess another way to write this whole equation is this. So we could write it as the force times radius is equal to plus minus radius times the rotational velocity times what we've called mass flow rate. So this is the short form of this equation. So this is torque. It's not the dividing it. This is torque, and this is the other part here. I've used uppercase M because we've used that for our mass flow rates. And the utility of this is we can also get the power. Perhaps I should use this as P dot. Power is equal to the torque on the shaft multiplied by the rotational velocity. And just to be clear, I should probably define these things, that rotational velocity is equal to radius times rotation. Omega equals radians a second. So this is a velocity of the system, which I'll draw, which I guess I should have drawn. And 2 pi radians a second equals 2 pi omega equals rotations RPS. So sometimes you want things in RPM, rotations per minute, rotations per second. This rotation is dimensionless. Radians per second has no dimensions. Has 1 over seconds as dimensions. And multiplied by a length is a length times 1 over seconds is a velocity, which is v theta. So take that on trust. And so what I'm going to do now is I'm going to draw this vane in a way that we can now use it, and certainly in a way that you'll recognize it. So this is our result. So these are just standard results that we'll use in a second. So I'm going to use a radius for this is our vane. Actually, I'm going back on that. Get rid of that part. I'm going to do it different. Okay. Yeah, right. Yeah, this is better. Because it directly addresses our sprinkler problem. So you can kind of see a vein here. So the idea is that we have water coming in here at W1. So this is also, let me get rid of these and write them as P dot. And this is, P isn't a good number either. We'll get to it. W2, which we'll call theta. We'll have, am I using any color scheme? I can't remember. We'll have a force that's applied, which is really a force in theta. And we have an angle, theta, and a rotation rate, omega, which is defining the rate. And very straightforwardly, I guess this is also a radius, so the radius that we talked about. And so if you write the expression that we have, I'm not going to derive it because we've just kind of derived it, is that the force times the radius, or sum of, is equal to the sum of the radius times so this might look quite familiar, right? All we've done is to our linear momentum equation is we added an r on either side. We have to realize that the water is coming out of here at some rate. It's useful to realize that these are orthogonal to each other. And for our use here, we're going to be interested in looking at only the rotational magnitudes. And I suppose we can draw a velocity on this. Doesn't matter so much. And so in the same way we talked about when we started class today, we talked about you have to write the velocities of the control surface congruent with the Cartesian directions. And we chose this so-called right-hand rule of x, y, and z. The rule for rotational behavior is the hitchhiking rule, which is, this is the axis z, and this is the positive direction of rotation. It doesn't really matter so much, just so long as you do things relative to this rotational direction. So if you're looking down on this picture on the board, then z would be coming through my head, and the positive direction would be counterclockwise as we've drawn it. I guess I didn't finish this off. This is v control surface. So this is the vane that's coming in. So it's not like our Pelton Wheel where we're squirting water on the vane and it's moving. This is our sprinkler question where we're pushing water out of the hose from the middle of the sprinkler. It's going down the yoke to the end of the sprinkler, and it's coming out of the nozzle, one on each side, and it's zipping around to be able to have some velocity. And we need to be able to solve that system. And so this is the equation that we'll use to solve that. And I guess the only other thing that we might want to realize is that the power we get from this is going to be equal to the torque multiplied by the rotational speed. So 1 over seconds is this. And of course, this torque is going to be this term here. These two terms, right? And so long as we define these things in the right way, we can solve a problem. And so I won't do this in a vacuum. Probably it's easiest to do it with one of the examples. And so I'll just introduce the example. If you wondered what a cross product is, it's really just this. This is the idea that you have a radius to the point of action of a force. The lever arm of that force has to be the closest radius you have, which would be plus F. So in this particular case, the torque is equal to the force times the closest radius. And to get that, the torque is equal to the force cross product radius. So that's all this means. So the cross product is only that. And if you can remember back into your math, these are just the ijk coordinates of this. So the idea here is that you have a velocity of a fluid acting through this point and going in the minus x direction. The point at which it acts is a value of r from that. And so you just need to be able to construct this determinant where I, j, and k are the x, y, and z directions. The radii of these points are ri, rj, rk. And the velocities of the fluid are the velocity in the x direction, the velocity in the y direction, across the y direction, and the velocity in the z direction. And so the cross product is this multiplied by the determinant of this, which is this term here. You'll never have to use this, by the way, so in case you're shaking in your boots now. This times the determinant of this term times this term, right? Which is this term here. And then this term multiplied by the determinant of these, which is this term here. And so all it ultimately gives you is the value of, when you do all the math, is it's this radius multiplied by this velocity, which is orthogonal to this radius. And so you can go through it. I'm not going to go through it, but that's what it comes out to be. We won't use anything in that form. So now that I've caught your attention, this is what we'll do. We'll do an example just with a simple sprinkler. It comes out of the book, and we'll walk step by step through this and figure out exactly what's going on. So this is our geometry. This is water that comes into the center of our thing. The water comes in at 5 liters per second. So this is a value of Q. And of course that water gets divided up to 3 equal portions, which would be that 1.66 liters comes out of each of these because of continuity. And it then comes out of the jet, and we could calculate, if we had an angle on this that's theta degrees, then we have to do the calculations relative to the tangent, relative to this velocity in the theta direction. So this velocity in the theta direction is by drawing a line to the center here and making sure that there's a right angle here. So this line is tangent to the direction of rotation. And so that's the geometry that we're looking at. If this water comes in here and turns a right angle to go out through this and then out through this plane, because everything in this plane is perpendicular to everything in this plane, it can have no component in this direction. So we don't have to worry about the fluid coming in through here because it's orthogonal to the other ones. So just as in the case of the vein that was being pushed by water arriving in the vein and then going vertically upwards, we don't care about the water going upwards because we're only resolving in the x direction, and that velocity upwards is in the z direction, and its x velocity is therefore 0. So that's the rationale for this. And so what we want to do is be able to use the equation that we've just defined to be able to do this. So I could go through this, but I could also do it cold turkey and see how wrong I can get it by doing it live. And that's what the intention will be here. So this is quite, notability is quite good. It's going to draw me a circle. That's pretty slick, don't you think? And so the idea is this. So this is direct in the sprinkler. So this is W theta. I guess it could be coming out at W. Let's not worry about that. And in which case we'd want W theta is equal to W cosine theta, right? So we don't need to worry about that. So this is W. This is the velocity that's coming out of the nozzle. If the nozzle is angled at theta, then this is theta, and this would be W cosine theta, right? This length here. We have 3 of them. And what we're going to want to do is we're going to have to calculate the force times the radius is equal to the sum of the radius multiplied by the velocity theta plus VCS theta times mass flow rate. This is what we're going, again, this is equal to the torque. And so what do? We know that the flow rate Q, 5 liters a second. So what are each of these terms? We need mass flow rate. Mass flow rate is what? Mass flow rate equals the velocity theta multiplied by the density of water times the area of the nozzle. We could rewrite that as W theta times A times density. So this term here is automatically Q over 3, right? So velocity times an area is meters cubed per second. This is meters cubed per second. And so the one for each of them. So I guess let's make it easy on ourselves. So W theta is equal to Q over area times a third, right? Flow rate divided by the cross-sectional area of the nozzle is a velocity. It's a third of the flow rate. I guess we could probably write, out of each nozzle is coming a third of the flow rate, and that flow rate is divided by the area. Perhaps that's another way for us to write it. And we know what the flow rate is. We know what the area of the nozzle is. I think it was 18 millimeters squared. Each nozzle is 18 millimeters squared. So area equals 18 millimeters squared times 10 to the minus 6, right? 10 to the minus 3 10 to the minus 3 millimeters in a meter. Meters squared is 10 to the minus 6 for this. So we have that. We have our sine law. So I guess we could write this, that the velocity of the control surface is in this direction, theta. And so we can start putting this equation together. So it would be that for one nozzle, we would have force times radius is equal to the radius times W theta plus V CS theta times W theta area times rho. We can get W theta from that, so this is for one nozzle. So for three nozzles, we'd end up with, again, the force times the radius. For three of these, so it'd be 3 times R times W theta plus V CS theta W theta area times rho. And this, of course, is equal to our total torque, the sum torque for all three nozzles. And we can start substituting parameters. So I guess before that, we should probably think about what we said about our sign convention. So for mass flow rate, W is positive if it's out, right? Just to remind ourselves, right? So how we wrote this. Come back to this. Sign convention for mass flow rate. Positive it's coming out, negative it's going in. And for the momentum part, these first terms, they're positive in the direction that we're defining for our sign convention. And so hopefully this works out to be the right direction. And so if we do that on this, then I can write it on this. So this is positive when it's out. If we look at the sign convention in this direction, this is defined as our positive velocity. You know, the right-hand hitchhiker rule would be Z coming upwards right at me here, and this being positive rotation, hence this. So this is positive, and W now is also in the positive direction because it's coming in the direction of my fingers as they're wrapped around this central portion. And so in other words, the result for this would be 3 times a length. It would be equal to W theta plus VCS theta times a positive value of this, area and rho. So I haven't done the calculations, but we know absolutely what the velocity is. It's the volumetric flow rate divided by the area divided by 3 multiplied by 3, because there's 3 of them. We know the areas of the nozzles. Some of these things would cancel out, and we know this is the density of water. And we can do just as, I'm not going to do the numerical values of this, and we could do the 2 end member conditions. And the 2 end member conditions are, we either hold it static, so it's going at no velocity, and we can figure out what the torque is that we have to apply, or we can release it and allow it to go at 0 force, 0 torque, and figure out what the velocity is. And so if torque is 0, then again, that means that the only way we can get that to happen is if these, the only way the left-hand side can be 0, this can be 0, is if these cancel out from each other. And so W theta equals negative VCS. So that means that W theta is positive, so this has to be going in the negative CS direction. So it's going, this is negative VCS. Exactly as you think, right? It squirts out, and therefore, if there's no torque that's holding it static in the middle, it goes around clockwise. And the opposite behavior is if the velocity of the control surface is 0. And then if that's the case, then this term here goes to 0. And if that's the case, then the torque is equal to 3 times R omega theta squared area rho W. That's it. And I suppose we could check the dimensions on this to make sure that that's the right units. Always dangerous to do that. This will be the maximum velocity, so it's going to be meters. It's going to be meters per second all squared. It's going to be meters squared. It's going to be kilograms per meter cubed. And so meters cubed, meters squared gives us kilograms, meters per second squared. So I'm just splitting up this meters. So a kilogram meter is the force required to give kilogram meter per second squared is a Newton, and kilogram meter per second squared is a Newton, and so this is in Newton meters, equals force times a lever arm. Newtons times meters. So this is a torque, and then we know that from a torque we can get the power is equal to, which is up here, which is equal to the torque times the rotational speed, which is going to be equal to newtons per meter for the torque, multiplied by 1 over seconds, which is equal to Newton meters per second, which is equal to joules per second, which is equal to watts. So, we got it. And so this is just the other expression that we had at the top. We wrote both of these. So these are the two expressions we wrote. I realize it's confusing to use this term here, hence I swapped out this for P. But the shaft torque multiplied by the rotation speed, this omega has to be defined in terms of radians per second. So omega would be equal to which is equal to, I guess, VCS, right? Just kind of this. Everyone's very quiet and not moving very much. Is that a bad sign? So, do you want to go through it again or go through the example? The example has some real numbers in it, so perhaps it makes a bit more sense. But it's a bit more complicated because these are the same equations, but they're written a bit differently. And so the idea is, again, so we have water coming up through the bottom here. It turns a right angle, and so when it turns a right angle, we don't care about this portion here. We only care about the flow rate magically emanating at a flow rate here and coming out here. And so we only have this one to take care of. We've done the calculation with W coming out here. Could come out at an angle, and we could accommodate that. But if it comes out straight, then we know that Q over 3 comes out of this nozzle, Q out over 3 comes out of this nozzle, and Q over 3 comes out of this nozzle. If the velocity that it comes out at is equal to the volumetric flow rate divided by the area, then by throwing this volumetric flow rate in there, the velocity has to be equal to Q over 3 divided by area, which is exactly the number we threw out here, hopefully, this term here. That's all we're doing. So we're calculating the velocity that gets squeezed out of one jet has to be, it's relative to the nozzle. So irrespective of whether it's moving or whether it's not moving, it's coming out of the nozzle at this velocity W. That's our definition of W, right? The velocity that comes out of the hose or the nozzle. So this is what they have here. They've called it V out, and it's equal to this amount. And then they've merely substituted this into this expression for the case where VCS is equal to 0. So in other words, they don't have this term W plus VCS because they've assumed that this term here is 0. Hence this. This is the W term. This is the mass rate of flow term, which we've called uppercase M. And then we have the mass rate of flow that's coming out because we know the flow rate. We have the velocity, which is coming out, which we've called W. And therefore we can calculate the torque that we have just by throwing these components in. The reason that this term here crops up is because the real velocity out is just equal to this length here. This is equal to V cosine theta. So if it's coming out at the real velocity, the velocity that's tangential, which is all we're interested in, because we're like resolving in Cartesian coordinates, we're only interested in resolving in this tangential direction. That's the only one that makes any sense to us. It's our fingers showing the direction. And that defines this velocity here. So the maximum torque that we'd get would be this: a volumetric flow rate, the radius at which it's turning, the angle at which it's angled, an area of the nozzle, and the density of water. And the only interesting thing about this question is that they use this angle theta to be able to change it, to be able to see where the maximum torque is. And so you can do it by intuition as to what that torque would be. They do it at 3 different angles. If the angle's 0, so if the flow is in this direction here, if it's at 30 degrees, which is at this direction, if it's 60 degrees, this would be V60, V30, and of course V90 would be this. And just your intuition, I hope you wouldn't design a turbine or a sprinkler that would do this, because it wouldn't move. There's no net force acting tangentially, and so this wouldn't move. And therefore there'd be no torque. It would just sit there on its own without any force being applied. If you have 60 degrees, then the component of that force in this direction is the velocity here. And if you have 30 degrees, it's bigger. If you have 0 degrees, this is the maximum tangential velocity you'd get. And so you'd think that that's the maximum force you'd have to apply torque to stop it. And so they go through this and they do those calculations. For T-shaft at 30 degrees, it comes out to be, at 0 degrees, it comes out to be 231 Newton meters, force times lever arm. At 30 degrees, it comes out to be 200. And at 60 degrees, it comes out to be 116. And at 90 degrees, they don't do it, but you know the answer to that. It would be 0. So they do separately the magnitude of the behavior for when there's no velocity. And then they go back and do the equation for when there's velocity. Same equation. Shaft torque is equal to uppercase M times radius. We know these terms. But now this second term is pitting the flow velocity relative to the velocity of this control surface. So what we've called VCS, didn't do that. What we've called VCS is what they've called their U. And so you get a difference between these, and if you do the accounting for the negative and positive, it comes out to be this. I think it's easier the way we did it. And so this allows you to do the opposite. So now you can put this equal to 0. You know that when the only way this can be 0 is when these two terms are equal to each other because of this sign convention, a bit different from what we did. And so they can look at the velocity of this as it goes around. Again, you can use your intuition. If it's coming out sideways, it wouldn't spin. There's no net component in the tangential direction. So V9, so the torque, the velocity when it's 90 degrees would be 0. The velocity when it's 0 degrees again would be a maximum when it's tangential. And as you cycle through these various angles, it would be progressively less and less until you get to V 90 degrees. And if you go through their answers, they first of all do it for the force. Then they do it at 0 degrees. The rotational speed is 185 radians a second. Units of this are 1/seconds. Radians has no units. Important to remember that. So at 0 degrees tangential, it should be the maximum. At 30 degrees, it's smaller. 185 versus 160. And at 60 degrees, it's 95. And you know if this is T90, this is equal to 0. And omega for the 90 degrees case is also equal to 0. So that's it. So yeah, I understand they're not super easy concepts to get. There's a lot of accounting. in terms of what's going on. I think the way that we did it, personally, is most straightforward and cuts through all the nonsense. And really, you're just using, there's two equations we're using, and they're the two equations we denoted early on. It's this moment of momentum equation, which is just our linear equation plus a radius added into it, and power from the product of torque and rotation. And actually this would work out exactly the same as we did yesterday, Wednesday. When you're holding it and the torque is a maximum but there's no rotation, then the power is 0. When you're releasing it and it's rotating freely, so the speed is a maximum but the torque is 0, there's no power. And somewhere in between there, when this is finite and this is finite, you yield the maximum energy from the system, which is the same as driving a turbine. You have to have a load on it to be able to, and it has to be moving. If the load is on it but it's not moving, then it's not expending, it's not making any power. So look at those and see it. Yeah. These are, it's really the same analysis. You just have to be able to take account of this coordinate direction. So come back with your questions on Monday. So we've finished off one section. This is the last part of what we'll talk about in terms of weeks 4, 5, which is Bernoulli. 6 was conservation of mass. 7 is conservation of momentum. We're done. We'll talk about conservation of energy. So the thing that changes for us now is now we'll start talking about fluids which have real viscosity, and where the essence of their behavior is dictated by the fact that if you want to dimension a pipe or a pump to be able to pump fluid from A to B, viscosity is a real thing, and we have to talk about frictional losses. And so now we'll start doing that. So we'll do that starting week 8. Okay?